Hello! Hopefully you've read section 2.3. If you have not yet read section 2.3, you should do that. This is a big section. This is a section where we start to learn about derivatives, and a derivative is maybe the most important quantity that we learn about in Calculus 1, our first semester of calculus. Yesterday in class, we learned about limits and how to compute limits algebraically. And we'll see limits come up here again in a few short seconds. In a previous video, we talked about average rates of change. But now that we have the concept of a limit, we can talk about something called an instantaneous rate of change. With an average rate of change, remember, I want to know how quickly an object is changing, or some quantity is changing, over a finite time interval. And so in your book, they talked about average velocity, okay? I could measure how quickly a car is moving, right? If I know where it starts and where it ends in an hour, and how long it took to get there, and how far it went, I would know an average velocity that it traveled. But maybe I want to know like how quickly that car is moving exactly 10 minutes after it started, okay? And so in order to kind of focus in on that one instant in time, we need to use a limit. Here's kind of a standard computation for finding an instantaneous rate of change. Okay, in this example, this one's similar to 2.3 number 2. My function is a quadratic function. You learned about those already in this course. The function is g of t equals t squared plus 4t. And I want to find the instantaneous rate of change of this function at the moment when the t, we can think about it as time if we like, at the moment when t is 0. Okay, let's start this problem by graphing y equals g of t. All right, just to give us something to look at here. So this is, I'm going to graph it in the yt plane. My formula is t squared plus 4t. I see that it's a quadratic. The leading coefficient, the a, is positive, and so this parabola will open upward. If I want to find the y-intercept, the t-intercept here, I can set my function equal to 0. So 0 equals t squared plus 4t. I can factor out a t from both terms on the right-hand side. That gives us 0 equals t times t plus 4. And so here I'm seeing that my t-intercepts are either t equals 0 or t plus 4 equals 0. In other words, t is minus 4. All right, so this quadratic has these two t-intercepts, one at -4, the other at 0, and then it opens up, right? And so maybe roughly our quadratic looks like this. Try to make a careful sketch of it. What I'm looking for is, in this problem, is I want to know how quickly the function g is changing at this precise location. Right? Clearly this function is changing. It's decreasing over here, it's going down, right? And then it starts to increase. But I want to know how quickly it's increasing at the moment when t is 0. In a previous section, when we talked about average rate of change, we saw that an average rate of change is a slope of a secant line, right? And so if I had some point over here, right, maybe at -3, at t equals -3, right, I could form this secant line, all right, and I would know that the slope of this secant line is the average rate of change of the function over the interval like -3 to 0 in this case. But with instantaneous rate of change, this is not what I'm looking for. I don't want the slope of this secant line. Instead, in some sense, I want to know the slope of the curve at this precise location, at this one location. if I only have one point, I can't form a line, right? I need 2 points to determine a line. But as they talk about in the book, if you imagine that this point over here, maybe getting closer, right, to where we want to be, then we can still compute secant line slopes, but the slopes of these secant lines will get closer to the slope that we're kind of looking for at this one point. All right, so in your book, right, the notation for this is a bit messy, but let's think about this location right here, this other point, as having t-value like 0 plus h, okay? And so in this case, h is negative. The formula in your book for instantaneous rate of change involves a difference quotient, right? And so it's going to be the difference quotient for this point at 0 plus h and this point at 0. And so that's g of 0 plus h minus g of 0 over 0 plus h minus 0. But now, right, if I just had this would be an average rate of change. But I don't want average this time, I want instantaneous. And so what I need to do is I need to take a limit. In particular, I need to take a limit as this point gets closer to 0. To make that happen, I let the h value go to 0. All right? So I do a limit as h goes to 0 of the difference quotient that I wrote down here. All right, I'm going to move to the front board and we will actually compute this limit algebraically. So here it is. The limit as h goes to 0, g of 0 plus h minus g of 0 all over h, right? In the denominator, the zeros go away. I just have an h in the denominator. To do this limit, I should look at the difference quotient first. I should evaluate the difference quotient first, try to simplify, and then at the end I'll be able to do the limit by plugging in. So, what should I do? This is the limit as h goes to 0. When I do 0 plus h, really I don't need to write that 0, so let's write that as just g of h, and then minus g of 0 over h. Like we've seen a bunch of times now for a difference quotient in the numerator, you have values of the function. And so I need to go to the formula of the function, right? That was g of t equals t squared plus 4t. And then I'm plugging in the numerator, I'm plugging in two different things. First I'm going to plug in h, and then I'm going to plug in 0. So this is the limit as h goes to 0 of, when we plug in h, we get h squared plus 4 times h. And then we subtract g of 0. G of 0 is 0 squared plus 4 times 0 in parentheses, all divided by h. All right, algebraically this one is not so bad, right? 0 squared plus 4 times 0 is all 0, so that term is completely gone. In other words, we have the limit as h goes to 0 of h squared plus 4h over h. Like we've done a bunch of times, in the numerator each term has an h in common, so you can factor it out. Right? This is the same process every time we do it. We factor out in the numerator. When we factor out an h, we're left with an h plus 4. In the denominator, I still have an h. When I have an h divided by h like this, after factoring out, then I can cancel it. So what's left now? Now I have the limit as h goes to 0 of h plus 4. And like we saw with limits yesterday, after we've simplified to a point where we are able to plug in whatever number the variable is approaching, then we're going to allow ourselves to do that. In other words, at this point, I can sub in h equals 0. And when I do it, I get 0 plus 4. In other words, I get 4. Okay? So the answer to the question is that 4 is the instantaneous rate of change of g at the moment when t is 0. Another thing to note from this section, right? is a geometrical interpretation of an instantaneous rate of change. I said it a moment ago, and we looked at it in the graph. The 4 that we just computed here is a slope. It's not a slope of a secant line anymore, because we're only dealing with one point. But this number is the slope of the tangent line to the curve y equals g of t at the point 0, g of 0. All right, for the next example, we're going to compute a tangent line, right? The problem will be, here's a curve, find an equation for a tangent line to the curve. The slope, right, whenever we try to find an equation of a line, we need a slope and we need a point so that we can use the point slope formula. The slope of the tangent line is an instantaneous rate of change, like we just computed. Instantaneous rates of change are desirable quantities to compute in many different areas of life, and because of that, they are given special notation and terminology. Instantaneous rates of change, like we just computed, are called derivatives. In particular, here's equation 5 from the section. The derivative of the function f at the number a is f prime of a, right? This apostrophe here is called prime. So f prime of a is a limit as h goes to 0 of f of a plus h minus f of a over h, as long as the limit exists. We've seen examples where limits don't exist. But if it does, if this limit exists, that's the derivative of the function at that point a. Equation 6 in your book is a different limit. The limit as x goes to a of f of x minus f of a over x minus a. But they talk about in your book, and we can talk about this tomorrow if you like in class, this limit here is equivalent to the one with h, and so it is still f prime of a. Okay? We can think about these two limits as being just equivalent definitions for the derivative of a function at a point. All right, these formulas here should be memorized for sure. This will be on the final exam. All right, we're going to do number 32, 2.3 number 32, where we find an equation of the tangent line to a curve. The curve here is y equals f of x equals x cubed minus 4x at a single point, 1, negative 3. From your reading about polynomials at some point, you know that this function is a cubic. The leading coefficient is positive, and so I know that the basic shape of this cubic is, it's kind of like a sideways S, but it's going to start in the third quadrant and then end up in the first quadrant. This cubic is nice enough so that I can factor it in order to find the x-intercepts. And that'll help me get a sense of what the graph is. So for the x-intercepts, like we're used to, we set the function equal to 0. Each term now on the right-hand side has an x in common, and so I factor it out. That leaves us with x squared minus 4. X squared minus 4 is a difference of squares, and so I can factor that further. This is 0 equals x times x plus 2 times x minus 2 using my difference of squares formula. Okay, now I'm multiplying three things together to get 0, so it has to be the case that one of those three factors is 0. In other words, either x equals 0, x equals negative 2, or x equals 2. So I'm getting three x-intercepts. At negative 2, at 0, and at positive 2. And then because I know the basic shape of this cubic, right, oops, I'm going to sketch it. It's something basically like this. Okay, it's a rough sketch for what this cubic looks like. I don't know exactly where 1 is here. I'm not sure exactly what the scaling is on my axes, but let's say that 1 well, when x is 1, the y value is -3, and so maybe, right, that maybe it could be the min, might not be the min, but let's say -3 is here, and then x equals 1 is up here. All right, so I'm looking for the slope, I'm looking for an equation of the tangent line to the curve at this point. Right, and so when we're thinking about tangent lines, we're thinking about like a line that sort of just barely kisses the curve like that, right? And so whenever I write down a formula for a line, I need to know two pieces of information. I need to know a point that the line goes through, but I know that already, right? The problem told me that. The problem told me that I want the tangent line at the point 1, -3. I also need to know the slope. This time it's the slope of the tangent line. And what you've read about in your text is that to get the slope of the tangent line at a given point on a curve, what you should do is compute the value of the derivative of the function. Yep, we're calling it f. So I want to know f prime of 1. Okay, I want to know the value for the slope here. I want to know the value of the derivative at the point. Okay, in other words, at x equals 1. So, we could do this with either equation 5 or equation 6. Maybe I'll use equation 6. So, the a in this case is 1, because that's where I'm trying to find the value of the derivative. And so, equation 6 with a equals 1, I'm just plugging in, but what it is, it'll be the slope of the tangent line, it'll be f prime of 1, and what it'll equal from the definition is the limit as x goes to 1 of f of x minus f of 1 divided by x minus 1. Okay, so if you compare this with equation 6, right, equation 6 has an a here, it has an a here, it has an a here, it has an a here. So it's the same formula, just with a equal to 1. All right, so a difference quotient. I told you these are going to keep coming up, and they do, right? We can do the difference quotient, and then at the end of the day, after we simplify, we'll try to do the limit as x goes to 1. So, limit as x goes to 1, you should write that notation every time until the very end when you plug in the 1. After you plug in the 1, you don't write LIN anymore. All right, so what's f of x? F of x is just the formula for the function. And so in this case, it's x cubed minus 4x. And then I have to subtract another value of the function in the numerator. So in parentheses, right, to get f of 1, I should set x equal to 1 in my formula. Okay? When you do that, you get 1 cubed minus 4 times 1. All of this is divided by x minus 1. Okay, let's simplify. Here's the limit as x goes to 1. In the numerator, we have x cubed minus 4x. And then inside the parentheses, I have 1 minus 4, which is a -3, but it's being subtracted. So that turns into a plus 3. In the denominator, you have x minus 1. At this point here, I need to keep simplifying, right? I can't plug in x equals 1 yet because it would make the denominator 1. But if you check, if you were to plug 1 into the numerator, you would get 1 minus 4 is -3 plus 3. You would also get 0 in the numerator, which is a good sign. 0 divided by 0 is indeterminate, but it tells you that there's hope that the limit exists, and this limit does exist. What we have to do, and this is a bit of an algebraic mess, I'll show you the details real quickly in a moment, but I need to somehow factor this cubic in order to get the x minus 1 term in the denominator to cancel. All right, I'll show you what the factorization is, and then we can think about how to get it in a moment. It should be something that you saw in pre-calculus. So, it turns out that the numerator can be factored as x minus 1 times a quadratic x squared plus x minus 3. And again, I'll show you where that comes from in a minute. In the denominator, I have x minus 1. Okay, typically with computations like this, for us, we will be able to factor. We will be able to compute these limits. All right, after factoring the numerator, now the numerator, the x minus 1 in the top and the bottom cancel. And so now I'm left with the limit as x goes to 1 of x squared plus x minus 3. And like we're used to, if we can plug in to get the limit, we will. And so in this case, I plug in x equals 1, so I get 1 squared plus 1 minus 3. In other words, I get 1 plus 1 is 2 minus 3, I get negative 1. And what does that equal? If we follow the equal symbols back up, we just found out that the slope of the tangent line is negative 1. At this point, we're basically done with the problem, okay? Because if I have a point and I have a slope, I can write a formula for a line. And so the tangent line to the curve, to that cubic at the point 1, negative 3, has the formula y minus the y coordinate of the point, so y minus minus 3, and then that equals the slope, which we found is negative 1, times x minus the x coordinate of the point, which is 1. All right, we can simplify this. This is y plus 3 equals minus x plus 1, and then subtracting 3 from both sides gives us y equals negative x minus 2. And so graphically, we might ask ourselves if this makes sense, and it does, right? I can imagine that this y-intercept is negative 2, right? That's the b from my simplified tangent line formula, and it looks like the slope is negative 1. So, the last part to talk about maybe is how to get this factorization of the cubic. You can do it with polynomial division, or maybe when you took pre-calculus, you learned about synthetic division. I did not learn about synthetic division, so I usually do polynomial division, okay? What I'd like to do here is I'd like to divide x cubed minus 4x plus 3. I'd like to divide that by x minus 1. Okay, I left some space between the x cubed and the minus 4x because for this algorithm here, I pretend that I have a plus 0x squared in this polynomial. So you sort of do this algorithm like you do long division of just numbers. The expression that I want to put up top here should be what I multiply by x to get x cubed. In other words, if I put an x squared here and then distribute it through, what happens? I get x squared times x is x cubed. X squared times minus 1 is minus x squared. With this long division algorithm, you then subtract. X cubed minus x cubed is 0. 0x squared minus a minus x squared is plus x squared. Right? And then we bring down these other terms. The next number up top, or the next expression up top, should be what I want to multiply x by to get x squared now. And so that should be plus x. And so x times x is x squared, x times minus 1 is minus x. And then we subtract. X squared minus x squared is 0, minus 4x minus a minus x is minus 3x. Bring down the plus 3. The last number that goes up top should be what I want to multiply x by to get negative 3x, and so obviously that should be negative 3. Negative 3 times x is negative 3x. Negative 3 times negative 1 is plus 3, and I see that my remainder is 0. And so what this algorithm is telling me is that the cubic x cubed minus 4x plus 3 equals x minus 1 times x squared plus x minus 3. Okay, this is how I factor the cubic.